okay, so now you know it's fucking collected over water. So you have to do some kind of subtraction in the beginning to find the pressure of your oxygen gas, right? Because they said you collected the gas over water, so you have to do some subtraction first to find the pressure of O2. All right, so it's collected over water at 45 degrees Celsius and 849 torr. Find the volume of oxygen gas when the temperature rises to 53 degrees Celsius, assuming the barometric pressure does not change. Okay, so the vapor pressure of water at 45 is 71.9, and the vapor pressure of at 53 degrees Celsius is 107.2. Now the barometric pressure does not change, but does the pressure of water change? Yes, at different temperatures, the vapor pressure is going to change. So that means the pressure of oxygen will also change. See right with that? So here we're going to notice that volume changes, temperature changes, and pressure changes. Okay? Because usually a lot of people just sit there and go, okay, 685 milliliters, 45 degrees Celsius. I want to find the new volume, all right? And it's at 53 degrees Celsius. And they see that the pressure does not change, so they assume that all we are doing is V1. We're doing V1 over T1 equals V2 over T2. That's what they assume that we're doing, because it says the pressure does not change. But since it's collected over water, there's a little trick there as well. Okay? Because your P total is supposed to be, let's see here. What's the P total? 849 torr. So over here, your P total is also 849 torr. Okay? But what's the problem, folks? We don't care about the wet gas. What we want is just the pressure of the gas itself, right? We want the pressure of the gas itself. So I already have the P total. In order to find the pressure of O2, I must subtract the vapor pressure of H2O and the vapor pressure of H2O here. I must subtract it. Okay. So the vapor pressure of H2O here at 45 is 71.9. Okay, and this one's going to be 107.2. Okay. So by that subtraction, I can figure out what the hell my answer is. So 849 minus 71.9. So that's 777.1 torr. And then here, 849 minus 107.2 is going to be 741.8 torr. You guys see that little trick there? This is the pressure. This is the pressure that you want. That's the volume. That's the temperature. So we got to add 273 to this. Okay, so 45 plus 273 is 318 Kelvin. And this one is 53 plus 273. 53 plus 273. So that's going to be 326 Kelvin. So we have the kelvins, we have the volumes that we're looking for, and the pressures. So now we can apply the general gas law. Aside from that, it's supposed to be P1 V1 over T1 equals P2 V2 over T2. We're going to assume that moles remain constant. Why? Why is the moles constant? No reaction. There's no reaction, so your moles should remain the same. They should be constant throughout the whole thing. So then we plug in what we know. The pressure is okay to be in torr because it only has to be in ATMs in which equation? In the PV equals nRT, right? It only has to be in ATMs and PV equals nRT. This has to be in liters in PV equals nRT, but we can plug in whatever it is in here now. So 777.1 torr. And the volume is 685 milliliters, all divided by 318 kelvins, equals P2, which is 741.8 torr, and V2 is unknown, all divided by T2, which is 326 kelvins. Okay, so I'm going to solve for V2, which is our final volume. So 77.1 times 685 divided by 318. So you multiply and divide, multiply by 326, and divide by 741.8. So your V2 would be 735.6 milliliters. Okay? So that's why it ends up to be C. Yes?
How do we get the P total?
The P total, you were told up here, it says is collected over water and at this temperature and that pressure. So 849 is your P total, which is a barometric pressure. All right? That's how you figure that one out. Any questions on that? Okay, good. All right. Then we move on to Graham's law here. It's Graham's law of effusion. All it says there is that if you're fat, you're going to run slow. Surprise! No. I run pretty fast. Not really. Just kidding. I don't run at all. So, first of all, when we talk about effusion, we need to know that the heavier gas itself is going to be slower than the lighter gas, all right? Because effusion is basically when a gas escapes out of a container, all right? When a gas escapes out of a container, that's going to be effusion, all right? So in general, the heavier gas is going to take a longer time to effuse, and the lighter gas is going to take a shorter time to effuse. So that's important that we realize that, okay? But this is, everybody look up real fast. This is Graham's law right here. This right here is Graham's law. All right? So if somebody asks you about Graham's law, it's just rate of 2 over rate of 1 equals the square root of gas 1 over the square root of gas 2. The time is just something that was added by your professors if, you can only use this if you have what? The same amounts. Okay? If you have the same amounts, then you can do the time. All right, the time relationship. Aside from if you don't have the same amounts, then you have to do something a little bit different. Okay, and that's in your practice problems to try out. I'm not going to do one today. I'm going to do one that's most common that I see on the exam. All right. Now, one thing that we have to realize here, folks, is that let's just say the number on top is large and the number on the bottom is small. Okay, meaning the top value is high, the lower value is small. So that means gas 1 is very what? Is very heavy. Does everybody agree with that? It's very heavy. So that means gas 1 is very slow. And gas 1 takes a long time to effuse if you have the same amount. Does everybody agree with that? Okay. So gas 2 would be what? Lighter. Does everybody understand that? It'd be a lighter gas. So then 2 would take a shorter amount because all the numbers are smaller than the ones on top. And then the rate is going to be very fast for the gas. The biggest thing that you have to do here is just keep the things straight, right? For rate, it's inverse. For time, it's direct. Everybody agree with that? So that's important that you make that realization in this case. So if you read this question, and I know it looks intimidating, it's long as fuck, it's like, oh, I don't know. But it's okay. Effusion problems are not that bad. There's really only kind of one way to ask it really tough, but I don't think they're going to do that. All right? So a 5-liter sample of methane gas was placed in a container filled with a porous membrane. A quarter of the methane gas effused through the membrane in 36 hours. A 5-liter sample of oxygen gas was placed in an identical container. How many hours will it take for a quarter of the oxygen gas to effuse through the membrane? So are they the same amounts? Yes. So we can use our relationship. We can say the square root of 1 over the square root of 2 equals time of 1 over time of 2. Because you have the same amounts. Okay? That's the key there. Same amounts. And you're usually going to see that because they want you to do the time and they're going to be the same amounts. Again, if you want different amounts, right, and you want to see that problem, you can see that in your practice set to do at home. So first of all, we have methane, which is CH4. Okay, and it weighs about 16.05 grams per mole. And we have oxygen gas, which is O2, which weighs about what?